Alright, hello everybody, and today we're going to be evaluating this improper integral right here, integral from 0 to infinity of x to the n over x plus 1, where our n right here is some real number between -1 and 0. And we're going to be using complex analysis to do this, so let's dive right in. So complex analysis, first of all, if we want to evaluate this integral, we want to define for ourselves a complex valued function. Let's call it f of z. And our function, we're just going to take this integrand right here and turn it into a complex function. So it's pretty much just replacing all the x's with z's. So we're going to have z to the n over z plus 1. So we're accepting complex valued inputs right now. Alright, so we have our function f of z, and it would be nice if we can figure out where the poles of this function are, because if we know where the poles are, then we can use Cauchy's residue theorem in order to do some cool contour integral stuff with it. So immediately there's a pretty clear pole where z is equal to -1. So I'll just put right here poles. So our poles, we have one at z being equal to -1, because if you plug -1 into here, you're going to get a 0 on the denominator, and that's going to blow up, giving you a pole. And there's actually one more sneaky little pole on this function right here, namely at z being equal to 0. And the reason why there's a pole there is because, remember, n is a negative number. And if we have a 0 to a negative number, well, that's just 1 over 0 to the positive version of that negative number. And 1 over 0 is exactly undefined. So in fact, when you plug 0 into here, under the condition that our n is negative, you're going to get a pole. Alright. So we have our poles right here, and let's go ahead and define for ourselves a nice contour to integrate across. So I'm going to draw up a complex plane right here, like so. So this is our real axis, this is our imaginary axis, and let's just plot our poles in. So remember, our poles are -1 and 0, so I'm going to highlight them in red. So we have one right here, and one right here. So we have one at -1, and we have one at, let's put it right here, 0. And now we have to define for ourselves a contour. And with our contour, ideally we want it to capture this interval right here, the interval from 0 to infinity. But before we do that, I need to touch on one minor little thing, namely the domain for our argument. So the domain for our argument, we usually take the principal argument, which is between -pi and pi, but we can't actually use that in this case because we're going to be integrating across the branch cut, which isn't really a good thing. So in order to avoid that, we need to shift our branch cut a little bit. And also later we're going to be using a natural log, and we need to define for ourselves a domain for our argument in order for our natural log to be defined. So we want to define our argument of z, I guess I'll just put it right here, to be between, what was it, 0 and 2 pi. So we have the argument of some complex number z being in this domain right here. And if you plot in the branch cut of that argument right there, it's going to lie exactly on the positive real axis like so. So that's the branch cut for our argument like so. So we're going to be using this fact later on when we evaluate a couple of integrals. So with that out of the way, we can go ahead and draw up our contour. So we want our contour to kind of capture this interval right here from 0 to infinity. Usually when we do this, we'll just take the finite case of that interval, so the interval from 0 to r. But in this case right here, there's actually two things that we have to take care of. Because if we just draw the line from 0 to infinity, one, we're going to be integrating on this branch cut, which isn't really ideal. Second of all, we have a pole at 0, and we want to avoid that a little bit. So in order to kind of get around that, why not just define for ourselves a path that goes a little bit above the real axis like so, and that starts a little bit away from this pole right here. And I'm going to draw up another picture that kind of zooms into this one little spot. In the origin right there, we're going to have our pole at z equals 0. So we have a pole right there. Our branch cut for our argument is exactly on the positive real axis. And currently we have our line right here sitting somewhere like that. So we're going to be integrating that way. And we're going to kind of make clear of what exactly this path is later on. But let's just draw it like this for now. Okay, so we have this path right here. Let's just shorten it a little bit. And now we ideally, since we have these two poles right here, we kind of want to use Cauchy's residue theorem somehow. And since we have this pole right here at -1, we kind of want to enclose it somehow. So in order to do that, what we're going to do is we're going to be introducing a little arc that goes all the way around the complex plane. So that's going to look something like this. So we have a circle that's going to go all the way around the complex plane, like so. Let's just keep going right here. That's looking pretty good. And we're going to go all the way around, and we're going to stop right before we hit this real axis right here, because that's where our branch cut is. And we kind of want to rejoin back to where we started right over here. So in order to do that, we're going to go in like so, so just below the real axis. And with this pole right here, we actually don't want to enclose that pole. I guess it's just nicer to deal with one residue later on, so we might as well skip this pole right here. And to do that, we're going to be integrating around this pole like so. And we get this nice looking keyhole shape. I think this is called a keyhole integral, if I'm not mistaken. But yeah, that's the integral we're going to be working with. And in terms of the path, we're going to be following this general direction right here. So we're going to be going all the way around like so, back this way, and then around here. So that's the shape of our contour. So now if we zoom into this origin part right here, this is what it's going to look like. So we have the initial path that goes this way. We also have the path coming back which goes this way, and we have this little circle that goes around. Okay, so we currently have something that looks like this. And with this small circle on the inside right here, we're going to give it a radius of epsilon. So I guess I'll just draw it right here. This distance right here, we're going to call that epsilon. And later, we're going to be taking the limit as our epsilon approaches 0. And the reason why is because we want this very interval right here, this initial interval, to kind of match with the interval from 0 to infinity. Similarly, with this big circle right here, we're going to give this a radius of r, and later we're going to be taking the limit as our r approaches infinity, for the same reason, in order for this interval to just grow infinitely large to match this initial interval right here. So let's give these paths a couple names. Let's call this initial path right here psi1, and we're going to call this upper arc right here gamma. And so this gamma is going to go all the way around. Actually, I'll put it over here just to free up some space over there. And then we're going to go back onto this path, that's called psi2. And then we're going to go onto this little circle right here, let's call it little gamma. And this whole entire contour, let's call it C, okay? So in this picture right here, this path right here, this is our little gamma, this is our psi1, and this is our psi2, like so. Alright, so we have the general picture of our contour. Let's just write out a couple integrals. So we have the contour integral that goes over C. So we're going to be integrating across this whole entire contour, C, of our function f of z, dz. And we can decompose this contour up into each of these little paths right here. So first of all, we have the integral over psi1 plus the integral, and then over this big gamma right here, plus the integral over this psi2, so the path going back. Then we're going to add the integral over little gamma. And yeah, that's basically our whole entire contour, each of these four paths right here. And I've got a 1 right here. And this integral right here is actually the integral of interest to us, because when we take the limits as our epsilon goes to 0 and r goes to infinity, we're going to end up with this integral here actually. So we have this equation that we're going to be coming back to later on. Let's focus on each of these integrals one at a time. So first of all, let's tackle the integral, the contour integral over C. So contour integral over C of f of z dz. What exactly is that? Notice that we can use Cauchy's residue theorem on that, because our contour is actually only enclosing this one pole. This pole at 0 right here is actually outside of the region enclosed by this contour. So we're only concerned with this pole at -1. So Cauchy's residue theorem says that it's equal to 2 pi I times the sum of the residues inside of our contour. But the thing is, since we only have one pole, we only need to worry about one residue, namely the residue at z equals -1. And our function is z to the n over z plus 1, like so. And we can use the definition of the residue, that's just the limits, as our z approaches our pole, so z approaches -1, of z minus the pole. So we have a z minus -1, which is just z plus 1, times our function, which is z to the n over z plus 1. And notice the nice thing is, this and that will cancel out. And we're going to be left with a really easy limit to evaluate, which is the limit, 2 pi I times the limit as z approaches -1 on this thing right here. And nothing will really blow up, so we can just substitute -1 to the z right here, giving us -1 to the nth power. And usually we don't really like it in this form. Let's just convert this to polar form. So this is 2 pi I, -1 is e to the I pi, and we can just multiply that n onto the exponent like so. So this thing right here is exactly the value of our contour integral over c. That's one of the integrals evaluated. Let's just put everything onto the side right here. So I'll just put all the results on here. So contour integral over c of f of z dz, that's going to evaluate to 2 pi I times e to the I times pi times n, like so. And later we're going to be taking the limit as epsilon goes to 0 and r approaches infinity and all that. And actually when we do that, the value won't change because we're still enclosing this one pole at -1. And Cauchy's residue theorem says that we can deform the contour as much as we want, so long as this pole right here or all the poles initially remain inside of the contour, the value will still stay the same. So those limits that we're going to be taking later on won't affect the number of poles or what poles will be contained inside of C. So therefore, this contour integral will stay the same under those limits right there. Alright, so on to the next integral. Let's evaluate the integral over psi 1. So integral over psi 1 of f of z dz. What exactly is that? Well, in order to evaluate this, we need a better definition of our psi 1 right here. So let's go up a little bit, back to this picture right here. And what exactly is psi 1? Well, notice that it starts at this little point right here, and that point lies on a circle. So if we kind of zoom into this area a little bit, we're going to get a picture that looks like this. So we have this radius of epsilon right here, and we're going to introduce a new angle right here. Let's call it delta, for example. And this very point right here where our psi starts, it's going to have a height of, what is it, epsilon, and then this side is opposite, so we're going to have epsilon sine of delta, and on the bottom right here we're going to have epsilon cosine of delta. And later we want these two paths to kind of close in on each other a little bit. So later, pretty much we're going to be taking the limit as our delta goes to 0. This probably really isn't the correct thing to do, but what I'm going to do is I'm going to approximate epsilon times the sine of delta as just epsilon itself. Because you see, in the limit as our epsilon and deltas go to 0, this value right here will go to 0 as well. And we can do the same thing right here. In the limit as our epsilon goes to 0, this whole thing right here will go to 0 as well. And in fact, for the cosine, you can just approximate it to 1, because if you take the first order Taylor series of this cosine series expansion thing right here, it's just going to give you 1. The first term of the cosine Taylor series is 1, so it really doesn't matter. We can just approximate this thing as 1 for small values of delta. And yeah, same deal here, we can just approximate this to epsilon because, well, it's just going to go to 0 in the limit anyways. So what can we say about our path psi right here? Well, we can parameterize psi a little bit. So psi, we can do the parameterization z is equal to, and now our initial starting point is right here, and we're going to be moving along this path right here. So our real part, we'll just call it t. The t will vary along this line right here, and as for our imaginary part, we can just add I times epsilon. And we want our t to go between epsilon and r. So t is between epsilon and r, like so. Alright, so where can we go from here? Well, we can differentiate this z right here to get that dz is just equal to, well, derivative of this thing right here is just dt, because I times epsilon is just some constant. And now if we plug all of this stuff into this integral right here, as long as the definition of our f of z, we're going to get the integral. And remember, f of z was z to the n over z plus 1. So z will turn into this thing right here. So t plus I epsilon, all raised to the nth power, over z plus 1, but z is this thing right here, so we're going to have z plus this plus 1. I'll just write it as z plus 1 plus I times epsilon, and our bounds are between epsilon and r. And then we're going to multiply by dt, because dz is equal to dt. So we have this thing right here. And now we can just ask the question, what would happen if our epsilon and our r approaches infinity? Well, in limit, as our epsilon goes to 0 and our r approaches infinity, first of all, the bounds are going to change, so they're going to go to 0 and infinity. And then what's going to happen in the integrands right here? Well, epsilon will get smaller and smaller and smaller, meaning that our imaginary part will just become so incredibly negligible that we can just ignore it, leaving us with just t by itself to the nth power. And same goes for the denominator. This imaginary part right here will just shrink to 0, leaving us with t plus 1 times dt. And in fact, this is the integral we started off with. And actually, I forgot to do one thing. I always seem to forget to do this. Let's call this integral we had at the very start I. So I is equal to this integral right here. And we just found that the integral over psi, this integral is the same thing. We just had different variables, so this is still I. Alright, cool. So we can add this result to this little side notes right here. So I guess I'll just clean things up a little bit right here. I'll just write things a little bit more neater. So we can write contour integral over c is equal to 2 pi I times e to the I times pi times n. So that's the first integral, and we also have the integral over psi 1. So we're applying the limits to all of these integrals right here, so that's just going to give us I in the end. Alright, so that's 2 integrals done. Let's move on to the third integral. And the third integral is the integral over gamma of f of z dz. So in order to evaluate this same thing as before, what exactly is our gamma? Our gamma is just a circle of radius, capital R, that goes around the origin. So it's centered at the origin. And where does it start and where does it end? Well, it starts at this point right here, and it ends at this point. And we're going to be using polar coordinates to parameterize this, so we might as well figure out what angle it starts at and what angle it ends at. Well, in order to figure those out, we don't really need to do much actually, because we can just give those two angles new names. Let's literally just call the first angle A and the last angle B. So to parameterize our gamma right here, well, gamma is all the z's on R e to the I theta, where our theta is on the interval A to B, like so, where A to B are angles inside this domain for our argument right here. And we can differentiate both sides of this thing. So dz is equal to, this is just chain rule stuff, R e to the I theta, d theta, like so. And we can plug all that information into our integral. So remember this thing right here, I'll just write out the definition of our f of z. It was z to the n over z plus 1. And if we plug all that in, z is now r e to the I theta, and if you raise this thing to the nth power, you're going to get r to the n, e to the I theta to the nth power, over, and then we're going to have r e to the I theta plus 1, and dz becomes I times r e to the I theta d theta, and our bounds are between a and b. Okay, and what can we do from here? Well, let's actually just combine some stuff in the numerator a little bit and bring out this I. So this is now equal to, if we bring out the I as a constant, so I integral from a to b, we have these two r's right here. So r to the first power plus n, so n plus 1. And we also have e to the I theta, which we can combine with e to the I theta n, which will give us e to the I theta as a common factor, and then n plus 1 like so in the exponent, over, and we still have r e to the I theta plus 1 and d theta like so. And let's call this integral, I don't know, j for example. And we're going to be doing some estimations on j. And we actually want to show that j goes to 0 in limit as our r approaches infinity. So we're going to be taking absolute values of j, and I'm going to be finding an upper bound for this thing right here. Notice that this integral in this form right here, this is dependent on a real variable. So what we can actually do is we can kind of bring this absolute value inside of the integral using the integral inequality. Let's actually just bring this I back into here, and we can say that this integral is less than or equal to the integral from a to b of the absolute value of this inside right here. And here we're going to be taking absolute values of literally everything right here. So absolute value of I, that's just 1, so let's ignore that. And then let's take the absolute value of everything up here. And notice we can split the absolute values up right here as well. So absolute value of r to the n plus 1, that's just absolute value of r to the n plus 1 like so. And then absolute value of e to the I theta times some real number. Notice that this whole thing right here is a real number altogether because we're defining n as a real number and theta is a real variable. So that thing overall is a real number, and whenever you have e to the I times some real number, that's just going to give you some complex number on the unit circle, and the absolute value of that is just 1. So we can ignore that as well. And absolute value of the denominator, that's going to give us absolute value r times e to the I theta plus 1 absolute value d theta. So you have this expression right here, and we want to estimate this further. And I guess just one quick note, r is a really big number, a bigger positive number, so we can actually remove these absolute values. R to any power is still positive. And let's see, what can we do right here? We have some complex number plus another complex number inside of absolute values, and we want to approximate this. And one last thing we can use is the reverse triangle inequality. So what does the reverse triangle inequality say? It says that if you have some complex number, I'll just put it over here, if you have the absolute value of a minus b, that's greater than or equal to the absolute value of the absolute value of a minus the absolute value of b like so. And right away you might be saying, well, that's kind of useless because this is showing that this thing is greater than this thing right here when we want to show that this integral is less than or equal to something else. But the nice thing is this is on the denominator, so if we reciprocate both sides, take 1 over both sides right here, in doing so we're going to flip the inequality, and that means that we're going to have something is less than or equal to something else, which is what we want. So right here, we don't have this denominator in this form right here. We want something minus something. And in order to fix this right here, we can just change this to a negative 1, I guess. So we're subtracting off -1, and now we have some complex number minus another complex number. And now we can use this identity right here. So this is less than or equal to the integral from a to b of, let's say we have r to the n plus 1 still, and then we have divided by the absolute value of the absolute value of a. And what is our a? Our a is r times e to the I theta, and the absolute value of r e to the I theta, well, notice that this thing right here, that's just some complex number on a circle of radius r, and the distance that is away from the origin at any point is just r itself. So we have r, and then we're going to have minus the absolute value of -1, which is just 1, so -1 like so. Remember, r is a really big number, and if it's really big, then subtracting 1 probably won't make it negative, so we can just ignore the absolute values there. And now we're left with this thing times d theta. And now the nice thing is, this whole thing right here is actually independent of theta, so we can just pull out this whole entire integrand, just like as if it's a constant. So now this is equal to r to the n plus 1 over r minus 1, and then the integral from a to b of d theta, that's some random constant. Let's just call that constant kappa for now. Alright, so what exactly did we just show right here? If you kind of trace back all of the inequalities, you'll find that we have the absolute value of j being less than or equal to this thing right here. But j is exactly this integral right here, which is exactly the integral over gamma. So what we can actually conclude from this is that the absolute value of the integral over gamma, that's less than or equal to this thing right here. R plus 1, r to the n plus 1, over r minus 1 times some constant kappa. And later we're going to be taking the limit as our r approaches infinity, so we might as well do that now. If we take the limits on both sides, we're going to have the limit as r approaches infinity on the absolute value of our integral over gamma, and that's going to be less than or equal to the limit as r approaches infinity of r to the n plus 1 over r minus 1. And this limit right here, we actually need to use L'Hopital's rule, because notice n plus 1, let's see, n was between 0 and negative 1, which means that n plus 1 is between 0 and 1. So right here we have r to some positive real number, and if you take the limit on that, that's going to go to infinity. Taking the limit on the denominator, that's going to go to infinity as well, so we need to L'Hopital this a little bit. And well, this limit, that's going to be exactly equal to the limit as our r approaches infinity, differentiating the top and the bottom. I forgot a kappa right here, yep. If you just differentiate top and bottom, we're going to get n plus 1 times r, and reducing the power right here, we're going to get r to the n, all divided by derivative of the bottom, that's just 1. And of course our kappa is still there, and that's equal to, well, we can bring out all the constants. We can just call it some other constant, kappa 2 for example, and then we have the limits as our r approaches infinity of r to the n. And you might think this is going to blow up, but it actually won't, because notice n right here is a negative number. And if you define, for example, another constant, let's call it j. So if you let j be equal to negative n, that means that our j right here is, since we're taking negatives on both sides, we're going to flip the inequalities, and now j is between 0 and 1. So n right here is exactly negative j, and since we have negative, we can put that on the denominator, so r to the j like so. Since j is positive, so j is between 0 and 1, if you take the limit, this thing's going to blow up, leaving you with 0. So overall, if you take the limits as our r approaches infinity on our integral over gamma, it's less than or equal to 0. So that's quite interesting. So if this thing is less than or equal to 0, what does that mean about our actual integral? Well, notice that the absolute value right here is always positive first of all, which means that the only way for this absolute value to be less than or equal to 0 is if it's actually 0 itself. So this implies that the absolute value of our integral is equal to 0, and the only way for this thing to hold is if the integral is equal to 0 itself. I think I forgot to put a limit right here. There should be a limit there, and a limit here right here as well. So overall, when we take the limit as our r approaches infinity on the integral over gamma, it's going to give us a 0, and that's our final result for this integral. So moving all the way back up to the top, we can add another integral to our list right here. Integral over gamma, that's going to go to 0. I really should put arrow that goes to 0 in the limit. Alright, so that's 3 integrals done. We have 2 more left to go. So our next integral is the integral over side 2 of f of z dz, and this integral is probably technically the most difficult to evaluate. So let's just plug in the definition of our f of z, so that's z to the n over z plus 1 like so. And what exactly is the path side 2? Well, it's the path starting from some point, some really big point r right here, and it's going all the way into this point right here, and we can use our kinds of approximation triangle right here to say that this little point down here is epsilon minus I times epsilon. So what exactly is our side 2, we can parameterize it by saying z is equal to t minus I times epsilon. So we have a minus right here because our path is on the bottom right here. And we want our t to start from a really big number r and then going down all the way to epsilon right here. So t, I'm just going to write it like this in interval notation. It's going to be a bit weird. It's going to go from r and it's going to go all the way down to epsilon like so. And if we differentiate both sides, we have dz is equal to dt. So plugging all of this stuff in, we're going to have the integral. Z is exactly this thing right here. So we're going to have, let's see, t minus I epsilon to the n over z, which is t plus t minus I epsilon, but let's put the plus 1 first, and then minus I times epsilon, and then dz is dt. So we have dt like so, and our bounds is from r to epsilon. So r to epsilon like so. Alright, and you might think, well, this pretty much looks like the integral over psi 1. Let's take the limit as our epsilon goes to 0, and we're going to end up with I, or negative I, because our bounds are actually reversed. But this isn't actually the case. We can't just take the limit like that, because as I said before, it's a bit technical. This all has to do with the argument right here. So the argument is between 0, including 0, to 2 pi, but not including 2 pi. And if you were to take the limit as our epsilon goes to 0, what you're actually doing is, we have this path right here, and what you're doing is you're moving it closer to the real axis from below. And since we're going into the x-axis from below, it's not going to give us the same value as if we come from it above, because if we take the limit from below, the argument of all the complex numbers on this line right here will actually be 2 pi, where if we took the limit from above, the argument will be 0. So that's a subtle difference right there, but actually the two integrals are actually completely different. And with this integral right here, we want to rewrite it in terms of I actually. So we actually can't take the limit when it approaches from the bottom. We have to kind of rewrite this such that we can take the limit from the top. So it is a bit technical, it's a bit hard to wrap your head around. It took me a while to kind of understand how all this stuff with the argument works. But yeah, we have to rewrite this somehow to get rid of this negative imaginary part and turn it into a positive imaginary part. So in order to do that, we're going to be using natural logs. So how can we use natural logs to do that? Well, let's just take a look at the numerator first of all. So if we take t minus I epsilon to the nth power, if we kind of turn this into base e, we're going to get e to the n times the natural log of this complex number right here. So t minus I epsilon like so. Alright, and where can we go from here? Well, I've made a video on the natural log of a complex number. If you take the natural log of a complex number, you're going to get the natural log of the modulus of the complex number, so t minus I epsilon like so. And then we're going to add I times the argument of this complex number right here. So what exactly is the argument of this complex number? Well, that complex number, if you just draw out a little triangle, I guess the real part is just a t by itself right here, and we have an imaginary part of negative I times epsilon. In order to find the argument, let's just find this angle right here first, and that angle is, let's see, the arctangent of opposite over adjacent. So this angle theta right here is arctangent of epsilon over t, like so. But the thing is, we want our argument to lie in this domain right here from 0 to 2 pi. If we go 2 pi around and we subtract off this angle right here, that's going to give us the argument. So our argument will be 2 pi minus tan inverse of epsilon over t. And later we're going to be taking the limit as our epsilon goes to 0. And this thing right here will go to 0 as well when we take that limit. So I'm going to do another silly approximation here. We're going to say that this value right here is approximately epsilon, because it's really going to go to 0 anyways, and it's just a waste of whiteboard marker ink writing that out, and a waste of space as well. So just for simplicity's sake, we're going to say that it's 2 pi minus this angle right here, which we can approximate as epsilon, and we need another set of brackets right there. Alright, so that's pretty good, but why exactly did we do that? Well, the main reason why I did that was because of this absolute value right here, because notice the absolute value of a complex number is the same thing as the absolute value of its complex conjugate. So we have a negative right here. Absolute value of this thing is really the same thing as absolute value of t plus I epsilon. And notice, now we've generated a positive imaginary part, meaning that if we take the limit as our epsilon approaches 0, we're going to be approaching the real axis from above, which is quite nice. So now we can clean up all of this stuff a little bit. If we split up this exponential thing and all that, first of all, this part right here, we're going to have absolute value of t plus I epsilon to the n, so bring this natural log down again and cancelling and all that, and then we're going to have multiplied by, because if we split the exponentials or multiplying, let's see, we're going to have e to the n times I times this thing right here, so 2 pi minus epsilon, like so. And this thing right here is basically the same thing as this original thing we had right here, so we can just chuck this back in right here. So this is going to give us the integral from r to epsilon of the absolute value of t plus I epsilon to the n times e to the I times n 2 pi minus epsilon, like so. And I'm not going to write the denominator yet, because we're going to do the same thing for the denominator, because notice we have a negative imaginary part right here, which isn't ideal, and we're going to try and turn that into a positive imaginary part. So let's do the same thing over here. So t plus 1 minus I times epsilon. If you just do the exponential natural log thing on this, we can rewrite this as e to the natural log of this thing right here. So t plus 1 minus I epsilon. And what exactly is the natural log of this complex number? Well, it's going to give us the natural log of the modulus of the complex number, t plus 1 minus I epsilon, and then we're going to add I times the argument of this complex number, and just like before, we can draw up a little triangle. So the real part is t plus 1, imaginary part is minus I epsilon. We want to find this angle right here, and that angle is just tan inverse of epsilon over t plus 1, and we can approximate this to epsilon, because when we take the limits, well, this thing's going to go to 0 anyway, so we can just simplify it to epsilon, and we want the argument to lie between 0 and 2 pi. So let's take 2 pi and then just subtract off this angle. So this is 2 pi minus epsilon, like so. And if we simplify things a little bit, we can split the exponential. So this is same thing over here, and we can rewrite this as same thing as before. We can change this negative to a plus, and now we can cancel e and natural log to get absolute value of t plus 1 plus I times epsilon times, now we can split things up a little bit further. Right here we have e to the 2 pi I, and then e to the negative I times epsilon. So negative I epsilon, like so. And notice e to the 2 pi I, that's exactly just 1, so we can ignore that, and we're going to be left with e to the minus I epsilon, like so. So in fact, this denominator right here is the exact same thing as this thing. That's what we just found out. So now we have absolute value of t plus 1 plus I times epsilon, and then e to the minus I epsilon, like so. And yeah, that is pretty much all the transformations we need to do on this integral right here. So let's get rid of all of this stuff right here, and we can chuck on a dt at the end. Alright, so remember, the reason why we did all that is to get these positive imaginary parts right here, and that's exactly what we did. So now let's actually just do one simplification. Let's just switch these bounds right here. So now we want the bounds to go from epsilon all the way up to r, and we have to introduce a negative to counteract that. And now what can we do? Now, since we have positive imaginary parts, that means that when we take the limit as our epsilon approaches 0, we're going to be approaching from above, because our imaginary part is positive. And let's see. Notice that this factor right here, this weird exponential thing right here, that's independent of t, as well as this thing right here. So let's chuck those out to the front. So this is equal to negative e to the I n 2 pi minus epsilon over e to the minus I epsilon, like so. And then integral from epsilon to r of the absolute value of its t plus I epsilon to the n over t plus 1 plus I epsilon, like so, and dt. Alright, and now we can actually safely take the limit as our epsilon approaches 0, because now we're approaching everything from above. So in fact, when we take the limit as our epsilon approaches 0, this is going to be equal to, we might as well take the limit as our r approaches infinity as well. This is going to give us, first of all, this epsilon is going to go to 0. It's going to become really small, and that's going to leave us with negative e to the in times 2 pi, which we can write as 2 pi in. So 2 pi in, like so, divided by, epsilon's going to go to 0 right here, leaving us with e to the 0, which is just 1. So yeah, in fact, this whole thing actually just evaluates to negative e to the I times 2 pi I times n. And then now, let's deal with this integral right here. So the bounds are going to go to 0 and infinity respectively. And this imaginary part, that's going to shrink all the way down, leaving us with the absolute value of t to the n over this imaginary part's going to go to 0, leaving us with absolute value of t plus 1, absolute value, and dt. And notice on this interval right here, 0 to infinity, our t is always positive. So in fact, we can ignore these absolute values like so. So this is just t to the n. And this integral right here is exactly the integral we started off with. So this is actually equal to negative e to the 2 pi I times n times our original integral I that we started off with. So that's pretty nice. So now we can add that to our little list of solved integrals. So the integral over psi 2 is going to be equal to I, but multiplied by this extra factor of negative e to the 2 pi in, and then we have I like so. Alright, that is the fourth integral done, and now we're going to move on to the fifth and final integral before we put everything together. So, integral over gamma of f of z dz. Again, we want to show that this integral goes to 0, and I think it's pretty easy to do that. This is the integral over gamma of z to the n over z plus 1 dz. And what exactly is our gamma? Well, our gamma is exactly this circle traversed in the negative direction, and it's going to start at some angle delta, actually down here, which is 2 pi minus delta. So right here, the argument is 2 pi minus delta, because remember, we need to stick between this domain right here, and it's going to go all the way up to delta. So our gamma, we can parameterize it as z being equal to epsilon, because we're on a circle of radius epsilon, times e to the I theta, where our theta is between negative 2 pi minus delta, or just 2 pi minus delta, and delta. So it's going to go all the way up to delta in the end. And differentiating both sides, dz is equal to I epsilon e to the I theta. And plugging all of that information into our integral, this is going to give us the integral on this interval right here, 2 pi minus delta to delta. Z is equal to this thing right here, and raising this thing to the n, we have epsilon to the n e to the I theta times n over epsilon e to the I theta plus 1, and our dz is I epsilon e to the I theta. And we can combine a couple things right here actually, because we have these epsilons right here. So we have integral 2 pi minus delta to delta epsilon to the n plus 1 e to the I theta n plus 1 like so. And we also have this I, let's just chuck it right there for now. And yeah, this is accounted for, and when we have epsilon e to the I theta plus 1 d theta. Alright, and now we want to show that this goes to 0 by taking the limit as our epsilon approaches 0. And if we take the limit on this integral, I think it's safe just to chuck the limit inside of the integral and take the limit in there on the integrand itself. So if we take the limit on the integrand right here, this thing is going to go to 0, leaving us with a 1 on the denominator. So if we take the limit as our epsilon goes to 0, first of all, we're going to have the integral from 2 pi minus delta to delta. So we have our I right here, and let's just put this epsilon here, epsilon to the n plus 1, and then, e to the I theta times n plus 1 like so. And you see, when this epsilon gets smaller and smaller and smaller, remember n plus 1 is actually positive, so a small number to a positive number is still a small number. So this thing right here is going to go to 0, which just kills off the whole entire integrand, and that's going to really go to 0. So yeah, that's how you can prove that. The integral along little gamma goes to 0 just by taking the limit on the inside of the integral. So we have pretty much finished evaluating all the integrals. We have the final result that the integral over little gamma goes to 0 as well. Alright, so that was a lot of work. That took quite a bit of time to do, but now we can use all these results right here and plug it into this equation right here and try to formulate an expression for our I. So first of all, we have the contour integral over C, which is 2 times pi times I times e to the I pi n, being equal to integral over gamma 1 in the limit that goes to I, like so, and then integral over gamma, that goes to 0, integral over psi 2, that goes to this thing right here, so negative e to the 2 pi I times n times I, and then integral over little gamma, that just goes to 0, so we can ignore that. Remember, I was the thing we're trying to find out at the very start, so let's try to solve for I. Let's first try factoring. So 2 pi I e to the I pi times n is equal to I 1 minus e to the 2 pi I n, like so. And notice that we have two exponential terms. Let's try to turn that into a sine function somehow. So in order to do that, let's multiply both sides by e to the negative I pi n, which is going to cancel out right here. So now we have 2 pi I, and then multiplying both sides by e to the negative I pi n, we're going to have I, and then bring that onto the inside right here, we're going to have e to the minus I times pi times n, minus 2 pi I n minus I times pi times n. That's going to give us I times pi times n, like so. And yeah, notice right here we're almost at our sign, we're just missing a division by 2i. Luckily we have a 2i hanging on the left hand side right here, so let's bring that over. And this is pretty much in the form for our sign, except ideally we want a positive exponent right here and a negative exponent right here. So let's just switch those two. If we multiply both sides by negative and switch the order in here, we can just bring this onto the other side. Switching the order, that's all we're doing. And this is going to leave us with negative pi being equal to I times this thing right here. That's just going to evaluate to the sine of pi times n actually. So sine of pi times n. And if we isolate our I right here, that means that our I in the end is equal to negative pi over the sine of pi times n, like so. And that is the final result for our integral. So yeah, that was a lot of work for this one result right here, but that's going to save me a lot of time in a future video where I'll be actually using this result that we found right here. If you haven't figured out already, this is basically the Euler reflection formula. I'll be doing a quick video on that. But yeah, we've basically done most of the work right here. So overall, integral from 0 to infinity of x to the n over x plus 1. Remember that was our I, but our I was negative pi over the sine of n times pi. And yeah, that is the final result for today's integral. So I forgot to mention one thing at the very start, which was why our n was between negative 1 and 0. Reason being is just because of convergence, because if our n was 0, for example, right on 0, we're going to get x to the 0, which is 1, and we're going to end up with a natural log as an antiderivative. Subbing in 0 or infinity, that's just going to blow up. So at 0, if n is equal to 0, we're going to get a divergent integral. If we put n is equal to -1, we're going to get x times x plus 1 on the denominator. And if you partial fractions that and do all of that, you're going to end up with natural logs as an antiderivative. Plugging in those bounds, it's going to blow up as well. So this thing actually only converges if n is between -1 and 0. So that is the final result for today's integral. Hopefully you guys survived through this pretty long video. I don't even know how long it is, probably close to an hour. But yeah, hope you guys enjoyed it nevertheless. But yeah, up until next time, hope you have a wonderful day, and I'll see everyone later. Bye bye.